Hi there. As promised in the previous video on the TC66, I wanted to quickly cover how to use it as a multimeter. Why would you do this? The TC66 gives you an actual 5.5 digit accurate readout on volts from 5 millivolts to 30 volts, measures current up to 5.4 amps. You can use it to measure resistance, in particular in the milliohm range. You can measure power with 0.1 watts resolution and of course battery capacity in milliamp hours and energy in milliwatt hours. And it comes with a recording capability and a remote interface for PC and additional Bluetooth in the TC66C model. It's all DC only of course, but you can get all that accuracy and functionality for just $30 or £20 when I bought mine last December. This machine deserves to be used a lot more than just measuring USB interfaces. To do that, we need to make the connections more accessible, which I show here as these red and black terminals. And of course, we need to keep in mind that to get these accuracies, we need to set the PWR and PD switches to off and power the unit via micro USB either from a PC or a power bank. How would you do this in practice? You've already seen me measuring a battery voltage. This is the first case here. Note that you can use either the set of terminals on the left or right to measure voltage, it makes no difference. To measure current, you only connect the TC66 using the red terminals. It does not matter which way the current flows through the TC66, it will just indicate the direction with the arrow or minus sign in the recordings. Here's how that looks in reality. Note that in this mode you have to ignore the voltage and power readings because the voltage input is just floating and can pick up noise. It's not bad if you power the TC66 from a power bank, but it can get a bit more when connected to a PC, while the power supply providing the current is also adding some stray voltages into the mix. It doesn't affect the current readings, but it's kind of distracting. For power, you need of course all 4 terminals, and it comes closest to how the TC66 was designed to be used. It doesn't really matter which end is the power source and which end is the load. And of course, the TC66 will also accumulate battery capacity in milliamp hours and energy in milliwatt hours in this mode. This is how power measurement looks like. This lamp uses almost 23 watts, and as you can see, the capacity and energy accumulators are incrementing as well. The TC66 also tells us that it has an equivalent resistance of about 6 ohms, which brings us to resistances. As you have seen, the TC66 shows resistance directly, but limited to 1 decimal, which is really a shame because it has these highly accurate voltage and current readings, and resistance is really just dividing the voltage by the current. So unless the firmware is changed to fix that, to get more decimals, we must be content by reading the voltage across the unknown resistor and the current flowing and use a calculator or a spreadsheet to do the division. Unless you do the resistance calculation as part of a power measurement, as in the previous example, you will need a current limit power supply. The reason behind this is that on one hand you want sufficient voltage and current to get as high as possible numbers on both measurements to be able to calculate a meaningful result. But in doing this, it becomes very easy to overload the resistor and release its magic smoke. In fact, you need to stay well below that to avoid stressing the resistor and causing it to change its specifications. To help, I made this chart which plots all allowed voltages and resistance and current combinations that will load the resistor with 50 milliwatts or less. That should not cause any damage even when measuring a tiny 1/8 of a watt resistor. I'll make this chart available for download in my GitHub page, link in the description. How does it work? Basically, you pick a current, for example 1 milliamp, which is the dark blue line, and it shows that you could measure resistors of 10k down to 1 ohm and would expect to see a voltage readout of 10 volts for a 10k resistor and 1 millivolt for 1 ohm. Of course, for the TC66, the voltage should be more than 5 millivolts, better 50 millivolts to stay clear of the offset error, so 1 milliamp is not a current to choose to measure a 1 ohm resistor with any degree of accuracy. Instead, for such a resistor, you go upwards and see that the highest current to stay within the 50 milliwatts would be 0.2 amps or 200 milliamps, which should read 0.2 volts. As a rule, you need to have at least a rough idea what the resistance is before measuring it. If you don't, you can set the power supply to 10 volts and limit the current to 1 milliamp and simply use the resistance shown by the TC66 to figure out the rough resistance. Then, for more precision, you look up the approximate resistance and move up to find a more suitable current. If the resistance is somewhere between 1 and 10 ohm, you would use 10 and going up, pick 50 milliamps and set the current limit to that. This will produce more accurate values, giving you a better result. It works reasonably well even for very low resistances. If your power supply doesn't allow setting a current limit, set it to the voltage, 0.5 volts in this case, which would work equally well. Let me illustrate why this complicated procedure is important. I just said to measure 10 ohms, you should set the limit to 50 milliamps or alternatively the voltage to 0.5 volts. If you leave the power supply at 10 volts and no current restriction, the 10 ohm resistor would cause a current of 1 amp to flow and be loaded with 10 watts. Like here, measuring one of Banggood's finest 10 ohm 1% resistors. Let me just pause for a moment to divide 9.7444 volts by 1.0119 amps to get 9.63 ohms, which means it's almost 4% out of spec. That's a lot, even for these ones. Maybe it's because it's getting a little hot? Oh well, the smell of carelessly measured resistance. To do this properly, and especially for very low resistors, we need to subtract the resistance of the probes by connecting them and calculating the resistance. In this case, I picked 0.5 amp as a current. If you do the math, it comes out to be around 0.094 ohms. Then we connect the resistor. Incidentally, this one is red, yellow, silver, which means 2, 4 or 24. Silver means a multiplier of 1 over 100 or 0.24 ohms. 5% because of the gold ring. We use again the shown voltage and current and calculate 0.334 ohms. Now we have to subtract the probe resistance of 0.094 and end up with 0.24 ohms. Not too bad compared with the BM235 value of 0.2. While the BM869S says 0.22, the actual value according to the Agilent 3441A using 4-wire mode is 0.235. Of course, the TC66 was designed to be used within USB connections, and moving it outside that protective environment means we need to follow some rules to avoid damaging it. Firstly, the TC66, or rather the INA226 chip inside, is not protected against negative voltages. This is particularly dangerous because we have all been using digital voltmeters, and on those swapping leads is no issue. All you see is a negative sign. So we tend not to pay too much attention on polarity when probing. For the TC66, it is crucial to always apply the right polarity. Secondly, although the INA226 could measure up to 41 volts, the datasheet warns not to apply more than 36 volts. Again, if you are not certain of the voltage, it may kill your TC66. Both the negative and overvoltage damage could also happen through transient and spikes, for example back EMF from switched inductive or capacitive loads. Lastly, the TC66 is designed for a maximum current of 5 amps. It can measure up to 5.4 amps and it wasn't damaged by a few seconds overload of 5.8 amps, but as a rule 5 amps is the limit. The question is, can the fixture that connects the TC66 to the probes add some protection against mishaps that violate these rules? Sounds easy and straightforward, but it turns out it isn't, because the whole point of using the TC66 is to take advantage of its accuracy, and any protection method must not compromise that. To avoid damage by negative voltage, the standard method is to insert a diode. I'm only showing one side here for simplicity. Anyway, while this works of course, it is unacceptable. The voltage drop across the diode causes an error of up to 0.7 or 0.8 volts. It can be reduced of course, but even with a Schottky diode, there is still a significant drop. The flaw of the simple diode method is the voltage drop in the forward direction. That can be zeroed by using an N MOSFET. When polarity is reversed, the gate is low and the body diode blocks, while at positive voltages, the FET with its extreme low on resistance of a few milliohms eliminates the voltage drop, and as a FET there is practically no gate current. This works absolutely great, but only as long as the positive voltage on the gate is sufficiently high to turn the FET on. At 5V input shown by the blue meter, the output on the red meter is practically identical within the accuracy of the meter. Reversing the input voltage and all we get is 60 mV of leakage, which is tolerable. But watch what happens when I reverse the voltage back to normal and lower it. Very soon you can see the red meter showing significantly less than the blue meter because the FET is no longer fully turned on. Unfortunately, that rules this method out as well. I did experiments with additional circuitry that would use the voltage from the micro USB to turn the gate full on, even at tiny voltages, but that means you now have to sense the input polarity in that helper circuit, and that needs to be done starting from millivolts and without drawing any current to not reduce the input resistance of the TC66. It all got way too complex for something meant as just-in-case protection. Back to basics and a clamping using two diodes. One is a normal diode from the 1N400X family and the other a 30V Zener diode. The first question you may have is why the extra 1N4006, and it's true that the Zener diode acts like a normal diode in forward direction, so there is no need for a second diode. But this Zener has a rather high forward voltage of 1.2 volts, which would be the maximum negative voltage experienced by the TC66. The 1N4006 is much better and clamps this down to about 0.8 volts. Sadly, we can't use a Schottky diode to reduce it further because their leakage current is too high, but the TC66 seems to cope with minus 0.8 volts. The next question is what happens to the diodes while they clamp? That is, if you either reverse the voltage or exceed 30 volts. In either case, potentially lots of current flows, which will destroy the diodes in milliseconds. An obvious way out is to add a fuse. To decide what fuse, we need to look at what the diodes can handle. The 1N400X series is well known and can deal nominally with up to 1 amp, which should be plenty to melt a fuse. The Zener diode needs more careful study. The 1N5363B is quite a beefy diode. The good news is that its leakage is fairly low, and even at the quite high voltage of 22.8 volts is still a maximum of 0.5 microamps, but probably quite a bit lower in practice. Its current capability is the worrying part. If we take the maximum Zener voltage of 31.5 at the nominal current of 40 milliamps, it's already dissipating 1.3 watts. The maximum current allowed is 158 milliamps, which pushes the power up to 5 watts. There's also a surge current specified at 3.7 amps, which according to this node is a non-repeating square wave with a pulse width of 8.3 milliseconds. That time isn't of much help, but we can extend it to up to 1 second as the node says. If we go up close to the 30V line and hit the 8.3 millisecond curve, we see the roughly 3.7 amp on the left. Doing the same for the 1000 millisecond curve, and the non-repetitive surge current allowed is still about 1 amp. Incidentally, in case you are wondering where the strange 8.3 milliseconds come from, it's half the period of a 60 Hz main cycle. I calculated what would happen using a 100 milliamp fuse or a 50 milliamp fuse. I spare you the details, but strange as it may seem, with a 100 milliamp fuse, there's a voltage window where you would kill the Zener diode faster than the fuse. Below about 35.2 volts and above 50 volts or so, you are fine, but in between a 100 milliamp fuse just takes too long to blow to prevent damage to the Zener diode. A 50 milliamp fuse would work because by the time the Zener diode is overloaded at about 158 milliamps or so, this represents already more than 3 times the rated fuse current, and although the fuse datasheet doesn't specify a time to blow for that current, you can extrapolate that it's likely quicker than 1 second. The trouble with that concept is that branded fast 50 mA fuses are very expensive. You are looking at 60 or 70 pence per piece, that is close to $1. Another problem with that concept is that you can't use it for current, power or resistance measurements because they would blow that precious fuse with certainty. I briefly examined using the Zener diode to trigger a thyristor, which would then short the plus rail to ground, allowing a much higher rated and cheaper fuse, but the thyristor leakage current is just too high. And a resettable polyfuse instead of a real one would be nice, but the resistance change is rather limited and won't work in this application. But that led me to consider a PTC instead of a fuse. Much like a polyfuse, a PTC increases its resistance when it gets hot, for example by the current flowing through it, but its resistance change is gradual and over a wider range. My initial worry was that the surge current would be too high for the diodes because the PTC takes time to get hot, but as you can see, for reasonable voltages like 50 volts it works just fine. On the left you see the effect of applying positive 50 volts to the input of the circuit below. The current through the Zener diode tops at about 100 mA, which is well under the limit of 158 mA, and then quickly drops to around 30 mA as the PTC heats up. The output voltage briefly rises to just below 32.5 volts, which is still well below the 36 volts maximum of the INA chip in the TC66. Reversing the input voltage to minus 50 volts produces the graph on the right. The current peaks at 200 mA, which is well within what the 1N4006 can handle, and then drops to 20 mA as the PTC heats up. The initial output voltage peaks at just above minus 0.8 volts and then settles to around minus 0.7 volts. The PTCs, the same V-shade type, I used for upgrading the degausser to demagnetize my UT210E clamp meter, link in the description. The final circuit as I implemented it is here and also on the GitHub page. You recognize that if the switch is in the lower position, the circuit is the same as I just showed. Thankfully, we only need one circuit to protect both inputs because as far as the voltage measurements are concerned, the right terminal is directly connected to the left. The 15 milliohms resistor between them is like a piece of wire. That circuit still won't do any good during current, power or resistance measurements, but at least it won't cost you a fuse trying. For these kind of measurements, you need to put the switch into the other position, which replaces the diodes and the PTC with a 5 amp fuse. So in that mode, there is no protection against overvoltage or polarity reversal, but at least you have overcurrent protection. Now, to be brutally honest, the input resistance of the TC66 isn't all that great, only around 300k, and with the roughly 300 ohms of the cold PTC, we now have a voltage divider of roughly 1 to 1000. Given the high precision of the TC66, that circuit therefore produces an error of 0.1%. That's plenty good enough for most everyday measurements, but when I'm after the highest precision, I leave the switch initially in the protection mode until I'm sure everything is wired up correctly, and then turn the switch the other way, so only the 5 amp fuse is in the circuit. The fuse's 20 milliohm resistance is so low that it doesn't influence the measurements. Another caveat is this. Similar to the fuse discussion earlier, a 5 amp fuse saves you from crossover currents like 15 amps or more, but won't do any good for say 8 or 10 amps. The TC66 will release magic smoke before the fuse does. If you are worried about such cases, you may want to replace the fuse with a 3 amp or 2.5 amp type. That way you can't measure 5 amps for unlimited time anymore, but gain a lot more protection against more moderate overcurrents that can still kill the TC66. Limited to the 4 use cases for the TC66, I find that the only time I'm casually using probes on multimeters is to measure voltages and resistance. For measuring current, I normally wire the circuit carefully in advance. This is why my circuit of the TC66 primarily protects against silly mistakes in the voltage mode. The other 3 measurement types require the TC66 to be carefully set up and wired in anyway, so the danger of swap polarities is fairly low. For resistance, you can use probes on that end if you like, and polarity doesn't matter. Finally, some pictures for my build. To be clear, it doesn't need to be like that. You can use any housing and arrange the handful of components in any way you like. The list of components I used is also on my GitHub page. Here you see the diodes, PTC, fuse holder, switch, and the little breakout board for the USB-C socket I mentioned in my TC66 details video. In that video I did not recommend it, which is true if you are looking for a generic breakout board, but here all we want is access to V-bus and ground, and for that it is well suited. For maximum current flow capability, you should bridge the V-bus and ground pads on both sides of the breakout board. For the other connection to the TC66, I choose to add a USB-A socket. I scavenged the USB-A socket from an old PC interface board. The housing is rather small, and for convenience I put the holes for the banana sockets on what would normally be the bottom. The advantage is that this means everything is mounted inside and no flying wires to components mounted on a lid are needed. Put together and with the bottom plate off, it looks like this. It is rather cramped inside, and a slightly larger housing would have been easier. To connect the TC66, you plug it in on one side and use the small adapter cable to complete the circuit. An alternative is to hardwire the cable into the box, in which case you do not need the USB-A connector. Apart from simplifying the build, this has the advantage of improved current capacity, but means you have to sacrifice a nice USB-C cable for it. At the beginning, you have seen me measuring the 3-volt battery voltage. Now let's reverse the probes to test the protection circuit. So far so good, but does everything still work? Let's reverse back to the correct orientation. Yes, no problem. And over voltage? I'm increasing the voltage above 30 volts as you can see on the red meter, but the TC66 stays safely clamped to around 32 volts. The parts list, schematic and resistor graph are on my GitHub page, link in the description of the video below. In there you will also find a link to my Patreon page. Consider becoming a Patreon to support the channel and get early access to videos and exclusive content. Thanks for watching.